All right, so let's get into some special right triangles. There's actually two special ones, and then we'll talk about the sine, cosine, and tangent of these angle measures that show up. But before we do that, as a real quick review, let's just kind of make sure we're comfortable with the basics of trig ratios in general. So again, with any right triangle, of course you have three sides in a triangle. Okay, you have two legs and you have a hypotenuse, where the hypotenuse is across from the right angle, always the longest side. And then it's going to depend on which angle you're talking about. So let's say we're talking about that angle up there. So that's a theta variable to represent an angle. And let's just say we're using that one. In that case, if that was the angle we were in reference to, the opposite leg would be the one all the way down here. You can kind of think of it's always the one all the way through the other side of the triangle. While the two sides that actually form the angle are going to be the hypotenuse and then the what we call the adjacent or next to, close to angle. And the three main ratios that we use are the sine of the angle, the cosine of the angle, and the tangent of the angle. And what they are is they are ratios, like a comparison to the lengths of any two of the sides in the triangle. And we'll see some more of this today when we do these special ones. But the way that these are always set up, the sine is always the opposite side length over the hypotenuse. Okay, the cosine of any angle is always the adjacent side over the hypotenuse, and then the tangent is always the opposite over the adjacent. Okay, and it's a way of finding, you can either find a missing side length using this, or you can actually find the missing angle if you know both of the sides that are in the other side of the equation. And of course the memory aid we always use is using the first letters so, ka, and toa. Okay, and that gives you a way to remember, for example, that sine is the opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. Okay, so again, what it allows you to do, you can, instead of having to use Pythagorean theorem, you can find a side length. If you only know the angle measure in one of the sides, then you can find the other side. And then, of course, if you wanted to, you could use Pythagorean theorem to find the third side. And we know the angle sum of a triangle is 180, so you really can find all the measurements. You can solve the entire triangle using some trig. Okay, but there are a couple special ones. Okay, these rules work for any right triangle, but there are two main ones that show up quite a bit that we need to know a little more detail on. And the first one is the 45, 45, 90. So if you have a triangle, okay, and you know that the two non-right angles are each 45 degrees, or I guess if you just knew one of them was 45, you could figure that the other one's also 45, because the angle sum again is 180. What ends up happening is every single time there's this pattern of what the side lengths, there's this ratio that they always fall in. And no matter what, okay, again, hypotenuse is over here, the two legs are always going to be equal to each other. Okay, and if you think about if those opposite angles are both 45 degrees, they're going to form the same length of a side opposite them. Okay, so that's one way to remember it. If that angle's 45 and that angle's 45, even from geometry, it's going to mean these side lengths, the legs are going to be equal. And if those are both x, they could both be 10 or 3 or whatever they are, they're both the same. The hypotenuse can be found using Pythagorean theorem, right? Wouldn't it be true? Let's just say, let me just call the hypotenuse c just to give it a variable. Isn't it true that with Pythagorean's theorem, the one leg squared plus the other leg squared would equal the hypotenuse squared? Okay, and if I want to solve that for c, x squared plus x squared is 2x squared. Okay, and in order to solve for c, when you do Pythagorean theorem, you end up taking the square root of both sides, right? So we take the square root. So c is going to equal the square root of 2x squared. Okay, and we can simplify that a little bit. We can separate the 2 and the x squared. And the thing is, the square root of x squared is just x, right? Now the square root of 2 we can't really do anything with. It's not a perfect square. It cannot be broken down. So it's really just the hypotenuse is going to be whatever x was times the square root of 2. Now we usually write it as x root 2. We put the x first. We don't want to get confused. If you write it this top way, the issue is the x under the square root or not? But if you write it this way, it's it's clear that the x is not under the square root. And if you think about it, what it's telling us is that, so the square root of 2 is about 1.4, a little bigger than 1.4. So no matter what, whatever the legs are, the hypotenuse will always be 1.4 times bigger, okay? Or to be more accurate, it'll be the square root of 2 times longer than whatever the legs are. Okay, so keep that in mind. That's going to be one of our special ones. We need to know that ratio. That's going to do some things for us in a bit here. Okay, just one super quick example just to kind of hopefully let this point sink in a little bit. Let's just say we had a triangle. Just do a real basic one. Let's say it's 45, 45, 90 again. And let's just say, for example, they told you that side's 6, and they want you to find this side. Okay, so you don't even have to do any SOHCAHTOA. That's the shortcut, right? We don't have to set up, the sine of 45 or the cosine of 45 equals 6 over x or whatever. You could do that stuff, and that's fine. But knowing it's a special triangle, you can kind of think about if those are the two angles that are both 45, I know that leg down there is going to be 6 as well. And we just showed in the previous problem that the hypotenuse will always be whatever the leg is, in this case 6, times the square root of 2. And you can actually leave it just like that. That's considered more exact. Now if you go into a calculator and multiply it out, it's going to be about 8.49 or something. And just depending on the directions, they might want a decimal approximate, or this would be considered an exact unrounded value. Okay, so we'll do some more examples in one sec. Let's talk about the other special triangle, which is the 30, 60, 90. Okay, and in this one I kind of did some of the work already. So basically the trick to get, the key, the answers, I guess, this is like the key down here. Okay, but to get to it, what I did was I started out with an equilateral triangle, if you see right here. And I said, imagine if each side was 2x. Okay, so you can see each side's marked as 2x. And then what I ended up doing was took the, let's see if I can get the purple here. I took this triangle, okay, and just drew it right there, okay? So you can see the right angle right here, okay, the 60 degree in the bottom right there. So that would leave this top angle to be 30 degrees. Okay, the hypotenuse ends up being 2x. Okay, and then the bottom side down here is it's half of the 2x from the big triangle. And then I just left this middle leg here as an unknown, called it b, and I did a little Pythagorean theorem down here and solved for b, much like we just did with the previous problem. And we end up getting what you see down here. Okay, this is going to be like the pattern or the formula for any 30, 60, 90 triangle. The shortest leg, okay, again, across from the smallest angle, you get the shortest leg. That can be anything, right? Let's just call that x. What this tells me is that the hypotenuse of a 30, 60, 90 will always be twice as long. It's always 2 times whatever x is. And then doing the Pythagorean theorem work over here, we found that the middle, or the longer leg, right, the middle side length of the 3 is always going to be whatever the shortest one is times the square root of 3. Okay, so we'll do an example using that in just a second too, and then we'll come back and do some SOHCAHTOA stuff with that, some shortcuts. Okay, but first off, let's go back to the 45, 45, 90 just for a second here. There's some very important values that we're going to need to use quite a bit, and eventually we will have these memorized. Okay, so start now. Start trying to let these sink in. But let's just fill in what we just saw a minute ago. The side lengths again. The 2 legs are x, and when we did Pythagorean theorem, okay, we get x root 2. So you don't have to do Pythagorean theorem every time. That was just to show you where the x root 2 comes from. Okay, but let's take this back now to sine, cosine, and tangent. Okay, because for these special angles, for 45s, for 30s, and for 60 degrees, we're going to know the sine, cosine, and tangent without a calculator. Okay, it's not going to be just some decimal that you type into a calculator. You're going to need to know these as exact reduced values. So let's think about it. Sine, right, sine is opposite over hypotenuse, right? So the sine of 45, now it doesn't matter which 45 we use. Let's just say we use that 45. Okay, the opposite side is x, and the hypotenuse this whole time is x square root of 2, right? Okay, now the thing is we want to reduce a little bit. Okay, what we can do to reduce a couple things is we can cancel out. The x over x cancels out. Now remember, it was 1x up there, so there's still a 1 over the square root of 2. And now we do need to simplify that a little bit. We don't leave square roots in the denominator, so what we need to do is do the square, multiply top and bottom by square root of 2. That's called rationalizing the denominator. And this will get us our final answer. The numerator is 1 times the square root of 2, and the denominator is square root of 2 times the square root of 2. So that would actually be the square root of 4, which is actually 2. Okay, so we're going to end up with root 2 over 2. And that's going to be what we're going to use for the sine of 45. Okay, now I want you, if you have a calculator, type in sine 45, and you're going to see it's telling you, make sure degree mode again, it's going to tell you 0.707. Okay, that is exactly what the square root of 2 divided by 2 is, but we're going to keep it as the exact value, the square root of 2 over 2, not the 0.707. Okay, because again, they're going to expect you to know these exactly. And these could always show up on a standardized test as a no calculator problem. Okay, that's just, we're supposed to know these ones exact. Okay, so let's do the other two. Let's do cosine and then tangent. So with cosine, okay, again, if we're using this angle as our reference, the adjacent side to that is x. The hypotenuse is still the x root 2. Okay, and what do you notice? It's actually the same as what we just did above, right? So if we do all those same reducing and simplifying steps, the cosine of 45 is also the square root of 2 over 2. Okay, so that's good. It's the same thing. And then probably the easiest one of all this stuff, or one of the, yeah, this one I would say is probably the easiest. Tangent from 45, what is it? What's tangent? Opposite over adjacent, right? So the opposite leg is x. The adjacent leg down there is x. What is x over x? 1. Okay, so the tangent of 45, that should be your favorite one. If that one shows up, the tangent of 45 degrees, and you can check it on a calculator. Tangent of 45 always equals 1. Okay, and again, what that's telling you, it's telling you the ratio of the opposite to the adjacent leg is 1, because they're equal to each other, right? So the ratio is like 1 to 1. Okay, that's all trig functions do. I know it seems like this weird, you know, sine, cosine, what is this stuff? It's telling you what is the ratio of the side lengths. Okay. All right, so kind of have those written down somewhere. This page right here is very important. We're going to do the same thing with the 30, 60, 90. But these values, again, start, you know, coming up with ways to memorize them. You can always draw the triangles and, you know, derive them like this, but you're going to want to memorize them. And there's some good shortcuts coming up. But, again, these are going to be a big deal for the next few math classes you take and then through calculus and everything. So kind of get those synced in your brain here. Where it came from. They come from just knowing those side lengths. And maybe make some flashcards, you know, put sine 45 and then put root 2 over 2 on the back. And really, really spend some time on these. We're going to use them a ton. All right, so for 30, 60, 90, though, let's do the same thing. Let's label the triangle first. I like setting them up with the triangle when we're first starting. Okay, and if I drew the triangle this way, with the short leg being at the bottom there, that means that the small angle would need to be opposite it. So the 30 would be up there, and the 60 could be here. So when you draw the triangle, again, it's just kind of for your own notes, but make sure you make one of the legs shorter than the other. Okay, and then this would be the medium length. It would be the longest of the two legs. And then, of course, the hypotenuse over there. Because the way these are always set up is the short leg is what we call x. We kind of showed briefly that the hypotenuse becomes 2x. And then from the Pythagorean theorem, and this was the one that we already had worked out that I just went through quickly, but the medium leg ends up being x root 3. Okay, so let's think about what the sine, the cosine, and the tangent for the 30-degree angle is. Okay, so 30 degrees up top there, right? So the opposite over the hypotenuse. Okay, in this case, from the 30 degrees, the opposite side is that bottom leg down there, x. The hypotenuse, of course, in this whole thing is 2x. So x over 2x. Remember, it's 1x over 2x. The x's cancel. It reduces to 1/2. Okay, so the sine of 30 degrees is 1/2. You do it in a calculator, 0.5. You'll see it. Okay, the cosine for 30 degrees. Okay, again, going back to the 30-degree angle, the adjacent side is the x root 3. The hypotenuse, of course, is always 2x. Okay, reducing, similarly, the x's cancel out. We get the square root of 3 over 2. Okay, root 3 over 2. And then for tangent, tangent is what, opposite over adjacent. So from 30, the opposite again is x. The adjacent is x root 3. Okay, we're going to have to do a little simplifying here because, again, we have the square root in the bottom. If I cancel the x's, it becomes 1 over root 3. And, of course, we do need to rationalize that. Let's times top and bottom by root 3. And we're going to get our final answer of the square root of 3 over 3. Okay, so that's the tangent of 30. Okay, and then finally, you know what, actually I think I'm going to leave the 60 degree as part of the assignment for you. I'll do the first one for you. But using the diagram, we should be able to do the same thing. Just notice now, for the 60 degree, we are now focusing down here. Okay, so the sine of 60 degrees, the opposite over the hypotenuse, right? Sine's always opposite over hypotenuse. So in this case, the opposite is x root 3. These, you know, all these values written down somewhere, okay, and run through again where they will need to All right, so let's just finish this up with a couple of last quick examples here. You know, again, the 45, 45, 90s, I think we did one similar to this just a minute ago, but I added that one in. But again, if it's 45, 45, 90, and you know one of the side lengths, right, here's the 45, here's the other 45. Of course, the hypotenuse is over here. Again, with this one, just remember, if both angles are the same, that means both legs are the same. So that would be 6. And the pattern just shows that the hypotenuse is always whatever the leg is times that 1.4, which is the exact value of the square root of 2. Okay, the other special triangle, the 30, 60, 90, it might be helpful. Just label the side lengths again. Remember, the short side is always x. The hypotenuse is 2x. And the middle is x root 3. Okay, so just by studying those patterns, you'll kind of remember this. And now we should be able to find the unknown lengths. So if the hypotenuse was given, that's like the 2x side. That means that the short side is just 1x, or half of the hypotenuse, which would be 4. And then that would make this middle leg, x is 4, so 4 times the square root of 3. Okay, so again, with these, study those triangles, have those written down, have the be memorized, and understand what they're doing for us. Okay, just keep in mind, what happens sometimes is people get this new stuff in their head, and that's kind of what they focus on, and then a problem like this will show up. Like, take a look at this real quick. Let's say we want to find that side length over here, x. Now, this triangle, this is not one of the special ones, right? This is a 27-degree angle. It's not 30 degrees. Okay, so I mean, it's close, but not the same. So to do this, we would have to go back to the original SOHCAHTOA stuff, where the x is the adjacent side, the 16 is the hypotenuse, and we would just have to do the old, you know, the cosine of 27 degrees. Again, it's not a special value. It's not going to be memorized. This will have to be done with a calculator. And then you would just have to solve that for x by multiplying both sides by 16. And again, just need a calculator. This one we're not going to get an exact value for. We're just going to get a decimal approximate, okay? Because it's not a special angle. 27 is not one of the ones we should know. Okay, but this one, if you just want to verify, should be around 14.3. Okay, so don't assume they're all special triangles. You may see some problems again where they're not, and you just got to go back to your old calculator. All right, so I know, again, a lot of information in here. Take some time with it, look at it, and then maybe look at it a couple hours later or the next day again, and let's just gradually get these committed to memory. All right.